let's look at theorem 2.11 with 2 by 2 inverses. And what this is saying, first of all, we're talking about an arbitrary 2 by 2 matrix with entries A, B, C, and D. This tells you that A is invertible if and only if this thing, AD minus BC, is not 0. And it also has a second part that says if A is invertible, then the formula for A inverse involves this. So let's prove the right direction of this if and only if statement first. So we're going to assume A is invertible, and we want to show that AD minus BC is not 0. Well, we just had a theorem that says if A is invertible, then this augmented matrix is row equivalent to this other thing. Let's use that theorem. Okay, now let's actually do the row reduction here. Let's scale row 2 by A. Leave row 1 alone for now. Then we can clear out this AC by doing negative C times row 1 plus row 2 to replace row 2. Gives you 0 here, and then an AD minus CB here. And we know that because A is invertible, this thing here cannot be 0. Because if that's 0, this matrix A is not row equivalent to I. In other words, we know the matrix A must have 2 pivot positions in these locations, just like the identity matrix does. So that's got to be a pivot position. So that proves the forward direction of 1. But, hey, we already assumed A is invertible. Let's actually just prove 2 while we're at it and show that this formula works. Because we just showed that AD minus BC is not 0, so at least we know this formula for A inverse is well defined. And it's worth pointing out how this formula works. We have like the opposite of B and C. Those are just in the same location, just change sign. And D and A switch places. And we're also dividing by this AD minus BC thing. So hopefully we multiply this out and get the identity. And so, yeah, that was just using the row column rule there for all of these. Now, 2 of these are going to be 0. And the other ones are going to be 1 because dA is the same thing as AD minus BC. And this one's just written in backwards order. So when you multiply this in, you're going to get 1, 0, 0, 1. Sounds good? Let's check this works if we do it the other way around as well. Well, we had a theorem about how there's an associative rule with matrix multiplication, so we can go ahead and take that out. And do this on the front, like so. And using the row column rule, we're going to get AD minus BC here. And again, two of these become 0. And the others are identical to the thing in the denominator on the outside. So when you scale them all by this fraction, you just get the identity again. So this is kind of a weird proof because we're proving these two statements kind of at the same time. So just assuming that A is invertible means that this thing, AD minus BC, is not 0. And then from there, that means we can define this matrix like so with this denominator in it that's not 0. And we just showed that when you multiply that on either side of A, you get the identity. So that means that this is the formula for the inverse. And if we found the inverse, that means we've also shown that A is invertible. Just going from the fact that AD minus BC is not 0, that showed us how to get the inverse, which means we can conclude that A is invertible. So that also actually proves the other direction of part 1. Cool beans. So that is that proof. So theorem 2.112. By the way, the first two parts of this, the proofs are exercises. So we're not going to do those. But we'll prove the third one. Now, 1 says that if A is invertible, then A inverse is invertible, and the inverse of the inverse is A. Maybe no big surprise there. It seems like what it should be. Likewise, if A is invertible, then A transpose is invertible, and the inverse of the transpose is the same thing as the transpose of the inverse. Sounds reasonable. And 3 might be a little bit unexpected because when you have the product of A and B, given that A and B are invertible matrices, the product of A and B's inverse has them backwards. So to show that AB is invertible, we can just prove this part. We can show that this works. We just want to show that A times B inverse A inverse is equal to I, and also that B inverse A inverse times AB is equal to I. Because that's what it means for something to be the inverse. It's a thing that you can multiply on either side of AB and get the identity matrix. Let's just start with these things we already have here. We have an associative rule. We know we can move parentheses around, so we could write this as A times B inverse times A inverse. Maybe you see where this is going. B times B inverse is the identity. And we know anything times the identity is itself. And we also know that A times A inverse is the identity. So yeah, that part works. And the same idea works here. Either way you get the identity. So yeah, that shows that we have the inverse of AB. Okay, the way I like to think of this is that when you take like a transformation A times B and apply that to a vector x, I like to think of this as like putting on your socks and shoes. The thing that gets done to x first is you're putting on your socks. And after you have feet with socks on them, you can then put on your shoes. And if you wanted to undo this, so then you just get x, you just get your bare feet again, what would you do first? You would take off your shoes, right? And then take off your socks. So, yeah, that's why this is sometimes called the socks and shoes theorem. I got that from a good book by Robert Beezer in his linear algebra book. Anyways, let's look at theorem 2.13 really quick, and then we will call it a day. So this says if A is an invertible C by C matrix, then for any vector y in RC, the equation AX equals y has the unique solution x equals A inverse of y. The proof is pretty quick, but there are actually two things to prove. One is that it has this as a solution. So we want to show that this actually is a solution. And to do that, let's just substitute this in for x. And we have an associative rule. We can do the A times A inverse first and then multiply that by y. That gives you the identity times y, and we know the identity times any vector is itself. So that shows this vector x equals A inverse y is a solution. We also need to show that it is unique, that that's the only solution. To do that, we're going to suppose there's another solution. And what that means is that A times W equals Y is true. Now, since A is invertible, I didn't write assume that A is invertible, but that's assumed, right? We're all thinking it. That means A inverse exists. And you can multiply by it. And maybe you see where this is going. We can move the parentheses around. You get the identity matrix times W equals A inverse Y. And the identity times anything is itself. So that means W is actually equal to this solution. So if you have any other solution, it's not really another solution. It's actually equal to A inverse Y. And that proves that. Cool beans. There might be some tricky exercises here. As usual, it's always good to work in a place you can get some help. It's good to talk about what you're doing, and I will see you later.